Hi, my name's Stuart Nicol. I'm with the Aussie Metallurgical Society. I'm reviewing a paper on smelting today. So the particular paper I've picked this time is the distribution of various elements in copper smelting, written by Akira Yazawa, as well as some others as lead researchers. This one was written by Tohoku University, and this you can access this via OneMine. So all the Aussie members, you can go through the website, go to OneMine, you can find this paper. So this particular paper and the concepts here, some of the earlier concepts I learned about non-ferrous pyrometallurgy and the chemistry and fundamentals behind it. So this sort of underpins a lot of the concepts and stuff used for chemistry problems and understanding how smelters work in general. So this is really good. And so if anyone sort of reaches out and asks me to explain some of the chemistry of smelting, this is probably one of the first papers I send them. So while this is about copper smelting, any sorts of non-ferrous pyrometallurgy or ferrous pyrometallurgy, any sorts of distribution between molten phases, this is a really good read. You can see in other sorts of commodities, they sort of haven't picked up these sorts of concepts as much, and so they are behind the work here, which is sort of surprising because this is quite old research. So I'll sort of jump through some of the sections. I think my favorite one, of course, I really like the maths behind these things, is they've got some really good equations here. So you sort of have to read through these equations and puzzle out what's going on, but it's worthwhile. So when we're looking at smelting, we control the major phases through controlling the bulk system. So your feed to other sorts of ratios, whether it's oxidant or reductant ratio. You control that ratio to achieve a product target. But a lot of the other components, all the minor elements, this is they distribute between the various molten phases depending on what they call the distribution ratio. So a lot of the fundamental research talks about PO2, but industrial practice we talk about the product grades and product qualities. So when we're looking at matte smelting processes, nickel and copper, people talk about the matte grade, and in lead smelting, when you have a mixed bullion and slag system, people talk about the lead and slag, and other sorts of ratios there. So it all depends on what industrial process you have, all these different sorts of product qualities or targets. But a lot of the researchers talk about PO2. And the reason they talk about PO2 is because everything can be tied very, very nicely back to your log PO2 when you start to look at your reaction equilibrium, what goes on in chemistry. So whenever you do these things, you just have to convert from what you think about in industry and the approaches there and how you run smelters in actual practice. You then sort of have to do a bit of like a unit conversion as such from the industry thinking to your fundamental thinking. But when you do that, you get some really, really nice maths. So what happens is this distribution ratio. So this distribution ratio is somewhat fixed at certain sorts of conditions. So for the same product grades and slag targets, your distribution ratio does not change much at all. And it's because it all ties back to your composition. So the distribution ratio comes from reaction equilibria, and you can see here that it depends on your equilibrium constants and your activity coefficients. And so these activity coefficients will vary a bit with your composition of your phases as well as temperature. And your PO2, this only really changes with your chemical targets there. So everything all ties back really nicely to PO2. So really, if you are interested, really dig through the maths and try and understand the actual fundamentals as why this is. But this is probably one of the most important aspects when you're building a lot of these flow sheet simulations. So when you're trying to simulate smelting processes, this is probably one of the most important equations, and I do try and peg things and bring it all back here when I do a lot of the chemistry design and things there. But this is a really good one. So when we're also looking at the distributions, you can see it all ties back to PO2. And so Yazawa and everyone else, they then did some work. So what they did is they took some synthetic systems and re-equilibrated it, looked at the bulk systems, and they looked at how things start to distribute. And so you can see that they have these really nice relationships. So you can see in the equation above, if you have your activity coefficients don't change, your distribution ratio is a function of PO2. And so you get these really nice lines. And this lines up very, very nicely with all the experimental work they did. So the exact experimental techniques they used were somewhat older than the ones available here today. So some of the more modern research groups like PyResearch at University of Queensland, they have revised and updated these. These lines also will depend a bit on your bulk feed composition and some things there, because some of your slag compositions and things there will shift a bit. So this one here was only done, I believe, at silica saturation. I could be wrong. And other sorts of saturations. We've got one's calcium ferrite slag, the other's an iron silicate slag. And when you look at one's magnetite saturation, the other one's tridymite saturation or silica chrysobolite saturation. And you'll sort of sit within a bit of an area rather than on a line itself, depending on what your slag is. But these areas are fairly narrow. But have a look at those papers by UQ if you're interested. They're quite good reads as well. But you can see here as well they've shown these two things. So one's the calcium ferrite slag, the other's an iron silicate slag. And this is another important concept because you can see that, for example, lead, you can get vast differences in your distribution between your slag and your metal, depending on whether you've got the calcium ferrite or the silica slag. Whereas other elements, you don't see much of a split. So depending on your feed and what you have, you can adjust the element partitioning and how your overall smelting flow sheet works when you convert the different slag chemistries. And so this sort of helps explain that as well. And you can sort of have a look at these, just to have a bit of a gander and really sort of figure out and puzzle out what's going on. So you can see different elements sit differently, and so you can have a look there. Another interesting one as well is these lines do shift with your PO2. So the interesting one here, so a good example one here is tin. So you can see that this is the solid line, calcium ferrite, dash lines, iron silicate. So you can see that the tin preferentially goes in the slag for, that's the calcium ferrite, on the phthalate stays more in the other phase. But in this one here, it's opposite end for copper. So in this case here, you can see you can change the distribution and how the tin sits in your slag relative to your copper, depending on your slag system. And you also have this kick as your oxidation state changes. So these are really good charts. But yeah, this equation is really cool. So have a look at this, puzzle it out if you are interested, and have a look at the charts. There's another really good figure up here, which I think is very neat. And it comes down to the copper dissolution in your slag and your mat. So this is an older figure. More recent research has revised this one, but this figure does explain some interesting concepts, and that is the form of sulfur and how sulfur sits in your mat smelting processes. So I don't see this as much in other commodities which are sulfur-free, but those containing sulfur can dissolve in the slag as a sulfide species. So what happens is that when you've got a very pure iron oxygen sulfur system, you don't have that oxysulfide split. You've got a completely miscible oxysulfide phase. Under the right conditions, you can split them out into two separate molten phases, a slag and a mat phase. And you can that split is enhanced by adding things like silica to stabilize the mat and split that out, so copper to stabilize the mat, and other base metals to stabilize the mat, and on the slag and stabilize it with silica. And so you get that split and separation. It gets stronger under certain conditions. So in this particular figure, at these low mat grades, you've got a fair bit of copper in the slag dissolved as a sulfide, while over here it's dissolved in oxide. So you can see the increase in the mat grade, you're pushing that sulfur out of the slag and into the mat, and you increase in the phase separation and the miscibility gap as well. So I thought this was a really neat figure, but again, check out some of the more recent research out there, and they have revised this one, but this is a really neat little concept. There's some other really good figures in here as well. These ones are worth having a look at and understanding as well. These are really interesting because you can sort of use different sorts of relationships depending on where you sit. So I sometimes use binary phase diagrams to estimate activity coefficients, and you can look at these sorts of figures and figure things out as well. So they're really neat ones too. And there's some other neat maths in here. So this stuff is quite good as well. But yeah, this is a really good paper. I'd highly recommend to read. If you were interested, again, it's on OneMine. This particular paper is called The Distribution Behavior of Minor Elements and Copper Smelting Systems by Yazawa. So yeah, check it out. It's really good. And you can access this one through your OSIM membership. If you log in through the portal, go to OneMine, you can find it there. It's great.